next we will be looking into a diagram, like as I was telling in the last class, that this CPU burst size is a concern. So, if you do do a statistical study about the sizes of this this CPU burst and try to see like how many CPU bursts are of what size. So, in this diagram you can see that this if I in the x axis, so we have got this burst durations 0, 8, 16, 24, 32 etcetera. So, burst durations are increasing, and then on the y axis we have got the frequency, like in a typical program execution how many occurrences of such burst sizes are there. So, if basically what I mean is that maybe the first burst size is very large, the second burst size, then after that we have got some IO. So, this is an IO, then the next burst size may be of this size. Okay. So, these are all CPU burst, okay. And then this is another IO, maybe this is some IO here. So, if you take a typical execution of a process, then if we try to see like how many CPU burst we got of a particular size, then in this diagram you see that you get very few CPU bursts that are of larger size. Like here you see that after the burst size 8, the number of CPU bursts, so it has become almost it is very small. Okay. So, whether it is 0 or not, that is a debatable issue, but that whether that will depend on the particular program, but in general, so it becomes small, and there are a large number of bursts which are of lesser size. So, if you see this is the peak, so this is basically somewhere here, so which may be around say 2 or say 1.5 like that. So, that way the number of CPU bursts of small size, so that is very large, whereas so below this again it is small, because so if it is number of CPU bursts, size of CPU bursts whose CPU burst size close to 0. So, that is also very less. So, this is, but there are some CPU bursts which are just slightly higher than 0. So, this means that this particularly happens when when the program is just starting, then you have got maybe after initialization it goes into getting the input from the user and things like that. So, that way this CPU burst size is very small, and we have got this CPU burst here. So, after some there will be some CPU burst size for which the number of occurrences will be very high. So, here the number of occurrences is very high of those bursts, and rest of the then it will start decreasing. So, this is a histogram showing the CPU burst times that you typically get in a system. Of course, this situation may change. For example, if you look into a program which is computation dominated, then you will see that this part is small, but there will be some peak will be somewhere here maybe. So, that is you get number of CPU burst of size higher size to be more compared to the CPU burst of lower size, or maybe this curve may shift further. So, you may get a CPU burst behavior like this. So, as you are going, so these burst sizes are very high. You get some burst size which is very high and their frequency is more. So, this is particularly true when we have got signal processing type of applications, because then it will be doing lot of computation. So, that way it is high. On the other hand, this if you are looking into this IO bound jobs, okay, say database operations and all. So, this is the typical situation that you get. Okay, but in a so because the number of amount of CPU burst size is small for most of the bursts. So, that way we have got this situation, but again for a typical program we will get a mix of the two. So, both IO bound and CPU bound things operations will be there. So, that way this burst size will be changing. So, this is about the CPU burst. Now, whenever we are talking about a CPU scheduling policy, whenever the CPU becomes idle, the operating system must select one of the processes in the ready queue to be executed, because if it is not, then the CPU will be waiting idle, and that way the CPU utilization will drop. Okay. So, we do not want the CPU to sit idle. So, naturally the CPU scheduling algorithm, so it should select it should select one job from the ready queue and put it onto the memory, or put it onto the CPU. So, it should send it should give control of the CPU to the job, so that that job is executed. So, it is the operating system's responsibility to select among the ready processes and give the CPU to one of the ready processes. The selection, this particular selection is carried out by the CPU scheduler. So, CPU scheduler will do this thing. The ready queue may be ordered in different ways. So, for example, you may say that the ready queue I will order in terms of their arrival. So, when a particular job came, so so there are say 10 jobs in the ready queue. So, the CPU scheduler has to pick up one out of these 10. Now, if we keep the queue ordered in some fashion, then this designing this CPU scheduler becomes very simple. So, if the queue is ordered in terms of say their arrival times, if they are ordered in terms of arrival times, then we know that the first job that I have in the system is the oldest job. So, the scheduler can take this job and give it to the CPU for execution. Now, or maybe they are sorted based on their priority. So, we have got priority of the jobs. Then, so whenever a new job joins into this queue, so based on this priority, so this job will be placed somewhere in this queue. So, it may so happen that this job is the highest priority one, and as a result it comes to the beginning, and by pushing back all other jobs. So, in that case also this CPU scheduling policy, so it can take up the first job from the queue and give it a chance for execution by the CPU. So, this way the scheduling policy or scheduling algorithm will be made very simple, but the queue data structure will maintain in such a fashion that this scheduler can be implemented very easily. So, this ready queue may be ordered in different ways that helps in developing this CPU scheduling algorithm, and scheduling decisions may take place when a process switches from running state to waiting state, switches from running state to ready state, switches from waiting state to ready state, and when a process terminates. So, these are the points at which we may need to invoke a scheduler. Like a process was in the running state, so it was a process was running in the CPU. So, it was it was in a running state. Now, what happens is that this process wants to go to some IO operation. So, it wants to do some IO operation. So, it cannot proceed further. So, it goes to the wait state, and when this is going to wait state, then naturally the next process to be selected from ready state and put onto this one. So, the scheduler needs to be invoked at this point of time. So, that is the first point. So, when a process is running and it switches from running state to waiting state, the scheduler needs to be invoked. Or when a process switches from running state to ready state. So, it may so happen that instead of going from running to wait, so maybe it was running here, and due to some reason or the other, so this is it is put back onto the ready state, and this is particularly true if you have got a time shared system in which a job is given CPU for some time quantum only, and after the time quantum expires, so this job is taken back from the CPU, and it is the CPU is given to some other job. So, that way this job the process that was running here, so it is taken back and it goes to the ready state. So, in that case the scheduler has to select a job from the ready state and give it a chance for execution by the CPU. So, that way that job makes a transition from ready state to running state. So, that is why, that is the second point, that is when it process switches from running state to ready state, then also we may need to invoke the scheduler. Another thing that we have is a process was in a waiting state, and after some time this wait period is over. So, wait period is over maybe because of several reasons, maybe it was waiting for some IO operation. So, that IO operation is over, or it was waiting for some event to occur. For example, it was waiting for some child process to terminate, things like that. So, when this is happening, then this process when this event is over, event or IO is over, then it makes a transition to the ready state, and now it may so happen that this job that has come to the ready state is the highest priority one, and it is even it is a priority even higher than the currently running process. So, in that case this process has to be taken out of CPU and this process should get a chance for execution. So, as a result this whenever a process switches from waiting state to ready state, so then also we may need to take some scheduling decision. And finally, when a process terminates, so a process was running and it has finished its execution by executing all the statements. So, it terminates, so it ends or terminates. So, again the CPU becomes free. Now, I have to take some job and put it onto the CPU. So, that is some job from the ready state should go to the running state. So, when a process terminates. So, these are the 4 different situation or 4 different cases into which this scheduler has to come into picture and take appropriate action to do the scheduling operation. So, in case of situations 1 and 4, there is no choice in terms of scheduling. So, 1 and 4 we do not have any choice, a new process must be selected for execution, and there is a choice however for situations 2 and 3, like switches from running state to ready state or switches from waiting state to ready state. So, we have got a choice. So, how this scheduling algorithms can be developed, so that will be that decision we will take. But before coming to this scheduling can be thought about in of 2 different types. One is called preemptive scheduling, another is called non-preemptive scheduling. So, if you look into this all the scheduling policies, so you can think about 2 classes. One class is called non-preemptive and the other class is preemptive. Non-preemptive class means that the CPU, that is once the process has got the CPU, so it will be running it will be utilizing it completely. So, in non-preemptive class once the CPU has been allocated to a process, the process keeps the CPU until it releases the CPU. So, how can it release the CPU? As I said that if this is the code that the process is now executing, so all these instructions that are there, so they are some computational instruction. Now, after this it may be it is going into some IO operation. Okay. So, if it is going an IO operation, then the CPU can be released. Okay. So, that is one voluntary way of releasing the CPU. Other thing is that it is it was executing and the execution is over. So, this process has got no more statement to be executed. So, it terminates. So, in either of these 2 cases, so this process will be releasing the CPU, but there is no other way by which the CPU can be taken from the process. So, you cannot stop the CPU, you cannot stop the process at some intermediary point and take the CPU back from the process. So, you cannot stop the process in between. So, that is the non-preemptive scheduling policy. So, CPU is not preempted from the process until and unless it voluntarily relinquishes the control. So, that is the non-preemptive scheduling policy. For other category, we have got preemptive scheduling policy. So, in the preemptive scheduling it can so this means that you can take the CPU back from the process in between. Okay. So, it can create some conditions like something called a rest condition that it can create. Okay. So, we will see how it is. So, what can happen is, so this is a situation that there are 2 processes that share data. While one process is updating data, it is preempted so that the second process can run. Second process then tries to read the data which are in an inconsistent state. So, this is one problem. So, this can create some rest condition, because suppose I have got 2 processes P1 and P2. Now, if if this P1 has got some piece of code to be executed, and if I say that it will be taken out from here, okay, and then P2 gets a chance for execution. So, maybe P1 was updating an array A in this part of the code. So, it was updating the array A, which is 1 to 1000, there are 1000 entries in the array. So, which it was updating, and this after it has updated for say 255 elements, then at this point it is decided that the CPU will be taken back from P1. Now, if P2 is scheduled, then what will happen is that, and P2 it tries to read data for the array A. Then for the remaining values from 256 onwards, 256 to 1000, so it will get inconsistent values, the old values that it will get, which is not correct. So, that way there may be difficulty. So, which process gets chance earlier, which process gets preempts the other process, and at what point. So, in one case for the same piece of code, maybe the preemption is done at this point. In another run for the same piece of code, maybe preemption is done somewhere here. Maybe after doing this updation, after updating say 500 elements, then this preemption occurs. Then naturally outcome of this this situation, when P1 has executed up to this much, then P2 is executed, and in this case P1 has executed up to this much, then P2 is executed. So, these two cases the outcome will be different, and it is that is the race condition. So, two processes, they are racing between each others so that it can get access to the CPU. But if it does that, then because of this preemptive policy this has happened. So, if it was non-preemptive, then in either case P1 will complete its the total updation, then possibly it will go into some IO operation by releasing the CPU. So, here also it will go into an IO operation releasing the CPU, and then only P2 will get a chance. That was the situation for non-preemptive scheduling, but for preemptive scheduling we have got a different situation. Also, we have to consider preemption while in kernel mode. So, this is another very important thing, because in kernel mode of operation, so it is actually doing some critical operation. So, maybe for example, suppose a process has given call to the fork statement, okay, and as a result of fork, so it goes into the kernel mode of execution, and there it is updating the process table. It is a new process is getting created. So, it is updating the process table, PCB list and all that. So, all those important things it is updating. Now, in between the updation, if this process is preempted, in between, then another process gets a chance for execution, and that also does a fork operation. Then what will happen is that this process table may go to an inconsistent state, because we have got more than one process which are concurrently trying to modify the process table. So, that is a situation that has to be avoided. So, this preemptive scheduling, if it was not there, then of course, my kernel in the kernel I cannot have two concurrent executions of two processes. So, this non-preemptive kernel will help us in that way, but definitely it has got some other difficulties. That is why we do not make kernels non-preemptive, but preemptive kernel basically that helps, because you can respond to many other important operations. And so, this is the problem. So, we have got this race condition that can affect the system performance, and also interrupts occurring during crucial OS activities. Like it was for example, here suppose it was updating the process table and then an interrupt came, and then if it goes into that interrupt handling, then there again that interrupt routine, it may try to modify the process table. So, that can happen. So, that will lead to some difficulty. So, we have got this preemptive scheduling is fine. So, it is good that you can take back the CPU from a process and give it to some other needy process, that is good, but it creates lot of inconsistencies. It has the potential to create lot of inconsistencies. Virtually all modern operating systems like the Windows, Mac OS X, Linux and Unix, they use preemptive scheduling algorithms, because of the reason that otherwise the system throughput or becomes low, and you cannot be fair to a number of user processes. So, that is why it is they are all of them are made preemptive. Next, we will be talking about the dispatcher or the scheduler. So, this dispatcher, so this is the module that gives control of CPU to the process selected by the CPU scheduler. So, what happens is that suppose at present the process P0 is executing, at present P0 is executing, and due to some reason or the other, so P0 cannot proceed further. So, maybe it is because of this IO event wait, or maybe because of some so time slice expiry, whatever it is, suppose it cannot proceed further. So, in the and the scheduler takes a decision that now P1 should run. Okay. Now, this switch over from P0 to P1 is not that simple, because later on you would like to restart P0 from the point at which it stopped. Okay. So, so that way we have to save enough information, and so we have to save the context of the process. We have to save the context of the process P0 into somewhere in the memory, and we know that the context is saved in the process control block of the process. So, first thing that it has to do is the save state into PCB 0, and this process 1, when it is executing, maybe the process 1 executed to some extent previously also. So, it is also a half done process. So, you are trying to resume the execution of process 1 from the point at which it got suspended. So, that way again the PCB of process 1, it has got the information about the point up to which it got executed. So, from there it has to restore the state from PCB 1. So, this thing has to be done. So, this the current context has to be saved in PCB 0, and the context of PCB 1, content of PCB 1 should be copied and should be taken and copied onto CPU registers and all. So, that is the restoration of context from PCB 1. So, this is the additional thing that we need to do whenever we are switching the control from process P0 to process P1. So, this is done by the dispatcher, and this particular delay due to this copy and restore of these PCBs. So, that is known as the dispatch latency. So, definitely I would like to make this dispatch latency small, and there are different processor architectures that come up to reduce this dispatch latency. For example, in different processors you may find that we have got a duplicate set of registers, so that you do not need to save all the register values in the PCB, or so you can just note down the register bank which is allocated to this process. So, that way you can just so if it is, if the next process uses a different register bank, then you do not need to save the context of previous process into the PCB. So, that way we can think about different architectural support for this reducing this dispatch latency, but whatever we do, so this some small amount of time will always come into this switching of process, or switching from one process to the another. So, this switching context is important, then switching to user mode and jumping to the proper location in the user program to restart that program. So, these are the, so switching context, that is copying the content from PCB to CPU register, or from CPU register to PCB. So, this has to be done in the supervisor mode, because the user program should not be allowed to do this thing, otherwise the system may go into an inconsistent state. So, this way we have to do this switching of context in the supervisor mode, then it has to go to the user mode, and then we can start executing from that particular user particular program's point at which it was suspended. So, you can restart the program. So, the dispatch latency, it is the time taken for the dispatcher to stop one process and start another one. So, that is the dispatch latency, and this dispatch latency should be small. So, that is the idea. So, how can we make this dispatch latency small and all? So, that is an issue. So, that we will see different architectures. So, they are supporting different facilities by which it can be done. Next thing that we will be looking into is what can we consider, like how do you judge a particular scheduling algorithm, whether it is good or bad. Okay, so, there are several criteria that we can have for this CPU scheduling. So, first and foremost criteria is known as the CPU utilization. So, CPU utilization says that how much time the CPU has been kept busy. Okay. So, ideally, as I said, that we want that CPU should be utilized 100%, but again because of this reason that in between you have to save and restore these PCBs and all. So, these times cannot be reduced. Okay. So, some amount of time will always be spent. So, you cannot have this utilization 100%, but if it is not 100%, we would like to be very close to 100%, as close as possible. So, CPU utilization is a measure like keep the CPU busy as much as possible. Okay. So, how much time CPU is busy? So, CPU if there is no job to be done by the CPU, then naturally CPU will remain idle and that time will be wastage. Then the throughput, number of processes that complete their execution per unit time. For example, I can say that there are 5 jobs completed per unit time. So, the throughput is say 5 per second. So, per second there may be 5 jobs completed. So, throughput is 5 per second. Again, what we would like to do is the throughput should be high. Now, there is a question here. So, this throughput can be made high if the jobs that are executing are of smaller size. Then if their CPU bursts are small, then definitely I can complete a number of CPU bursts within a given time. So, the utilization, the throughput will be high. But at the same time, if you have got this burst size is very small, then there will be lot of time that will be wasted in the context switching. So, context switching will also take time. So, naturally throughput will not be exactly proportional to the number of jobs that are completed, but it will be also depend on the this extra context switching time that is needed. So, throughput is the number of processes that complete per unit time. So, instead of number of processes, so you can say it is the number of CPU bursts that are completed per unit time. So, when we will be using these terms interchangeably, that is the CPU bursts and processes. So, you should always keep in mind that we are actually talking about the CPU bursts. Then turnaround time, the amount of time to execute a particular process. So, turnaround time is, suppose we submit a job at time t equal to say at 3 at time t equal to 3 we submitted a job, and when this job is complete. So, that is the turnaround time. So, this is basically the clock time. So, you submitted the job at say 3 am and you got the result at say 3:30 am. So, in that case the turnaround time is 30 minutes. So, that way how much is the turnaround time? So, the time at which a job is submitted. So, a job makes a transition from this created to. So, when the job gets the status new, from there the time it gets the status terminated or over. Okay, so, till that state. So, how much is the total time needed? So, there may in between the job will be scheduled and descheduled several times depending on the policy that we have. So, that way we can have this this new. So, this entire time will come in the turnaround time. So, we definitely want this turnaround time to be small, because we want that more jobs be done. So, the users of the system, they should feel that okay, my job is not taking much time for execution. So, that is the turnaround time. Then waiting time. So, total amount of time a process has been waiting in the ready queue. So, as you know that we have got this thing, the processes. So, they are put onto the ready queue for execution and they are waiting in the ready queue. So, they are all in the ready state and all these processes are put onto the ready queue. Now, from here, so we are taking processes to go to the running state, and after some time the process may be coming back to ready queue directly, or it may be going to some wait state, and from the wait it joins back to the ready queue. So, both of them are possible, but ultimately what happens is that if the job is not complete, in either way, either via this path or via this wait state path, it joins the ready queue again. So, again it has to wait for some time in the ready queue to get the next chance of execution. So, next CPU burst will be coming when other jobs are over or something like that, depending on the scheduling policy. So, the amount of time that a job spends in the ready queue. So, that is total amount of time a process waits in the ready queue. So, that will be called the waiting time of the job, and naturally we would like to reduce this waiting time. And we have got another timing measure which is called the response time. So, response time is basically it is particularly important if you have got this time sharing system or multi user or interactive system. So, basically if I take the same example like finding the roots of quadratic equation a x square plus b x plus c. So, to start with, the program does some initialization and then it gets the input, it executes the input a b c. Many programs they start with they at the beginning it prints some message and with that it starts. So, there is some message to be printed and with that the program starts. So, suppose I give the program for execution, then how much time it takes to come to this first print statement or this first input statement, where some user interaction is involved. So, if it prints something, the user is able to see, okay, my program it is running and it has executed up to this point. So, it is giving the message, or if it is an input statement is there. So, it is asking for input from the user. So, user is getting the feeling that okay, the program is now asking for some input. So, that means my program is progressing, my process is progressing. So, that is the response time, the time taken by the request that was submitted until the first response is produced. It is not output. So, it is basically not the output of the program, like it has not given me the roots, but it has just given me the message that input the values of a, b and c. So, and that is the response time, and we get a feeling like how responsive is the system. So, how quickly the program is responding to the user's request. So, that type of situation is the time sharing environment, and in the time sharing environment we have got this response time as an important parameter. So, depending upon the environment onto which you are judging a scheduling policy, so one of the criteria may be important. So, maybe for interactive systems this response time is important, whereas we are not that much important, we are not that much bothered about response time. So, if you are doing say scientific calculations, so that way we may be bothered there about this throughput or the that is number of jobs completed per unit time. So, it is doing lot of number crunching. So, it is doing there. So, we will be looking into many scheduling policies and we will try to judge them based on this scheduling criteria, and that we will do in the next class.